So let's go on to some specific examples. There are 4 in your textbook. We're going to work all 4 of them. We're going to work them all using the ideal gas law, even though your authors do it a different way. Example 33.1. A fixed quantity of helium occupies 16 liters at 20 degrees C while exerting a pressure of 45 atmospheres. If the pressure of the gas is reduced to 20 atmospheres and the temperature remains constant, find the new volume. First, I'm going to write down the ideal gas law. And I'm going to recognize that I have 2 states here that we're looking at. There's an initial set of conditions and there's a final set of conditions. I'm going to call the initial conditions conditions 1 and the final conditions conditions 2. So I'm going to put subscripts beside the ideal gas law, and I'm going to write the ideal gas law a second time with a different set of subscripts. Now I want to make a set of observations. The first set of observations is that I have a fixed quantity of helium. What that means is that the number of molecules of gas and the number of moles of gas, N, does not change. So N in the red equation under the first conditions and N in the green equation, the second conditions, are going to be the same N. R is a constant, so the ideal gas constant in both equations is the same. Another thing they tell me is that the temperature remains constant. So what that means is that T1 and T2 are going to be the same number. Now, that number happens to be 20 degrees centigrade. I could convert that to Kelvin. It's going to turn out that that number is going to disappear. I'm not going to go to the bother at this point. The things that are changing are the pressure and the volume. So let me write down what the initial pressures and volumes are, and then see how the final pressures and volumes are going to be related. Now what I want to do is I want to do the same thing to one side of this red equation as I do to the other side of the red equation. And basically I'm going to divide the red equation by the green equation. This is kind of a trick if you want to think of it that way, but this is going to get me what I need to know. And now I'm going to divide things out that are equal. N on both sides are equal, R is equal, and T1 and T2 are the same thing, so they're going to go away. And what I'm going to see is that P1V1 is equal to P2V2. What am I looking for? I'm looking for V2. Let's solve that equation for V2. Now, you can see that I can feed in the numbers here, and I will find my volume in terms of liters. And it's not going to be important for me to actually convert these things to MKS units. So I'm just going to leave things in the units that they are. I'm going to feed in the numbers and come up with an answer. And what I find is that my new volume is 36 liters. In other words, if I remove pressure, the temperature stays constant, then the gas expands. And that makes common sense. If I take the pressure off a gas is going to expand. That's the first example. The other ones are done in a similar sort of way. Let's go to the second example. Example 33.2. A fixed quantity of ideal gas has a temperature of 42 degrees C, a pressure of 80 Pascal, and a volume of 2.0 cubic meters. What will be the temperature of the gas in Kelvin if the pressure is increased to 100 Pascal and the volume is decreased to 1 cubic meter? My gosh, there's a lot of stuff going on here. Again, think about the 2 different states, state 1 and state 2. Write down the ideal gas law, write down the numbers that you know, take the ratio of the 2 gas law equations, feed in the numbers, and solve the problem. That's how a lot of these things go. Here we go. This is the way it starts. Okay, so I know the initial pressure is 80 Pascal, the initial volume is 2 cubic meters. Since they're asking me about temperature, then I have to work with Kelvin temperatures, absolute temperatures. So I've converted the first temperature to Kelvins. The second pressure and volume is 100 Pascal and 1.0 cubic meters. Now I'm going to write the ideal gas law in a ratio form and put in the numbers. I can see that the fixed quantity of gas means that N is the same in both of those equations. The ideal gas constant is a number that is going to be divided out, and I can have an expression for T2 in terms of known quantities. So the N's go, the R's go, and I can write T2 in terms of everything else. And now I put in the numbers and put them in my calculator. And if I round to 3 sig figs, I get 197 Kelvin is the new temperature. In other words, the gas cools off as a result of all these processes that I did. Next example. Temperature of a fixed quantity of an ideal gas is held constant at 400 degrees C. The pressure was 4 times 10 to the 4 Pascal when the volume was 40 cubic centimeters. Find the final pressure if the volume is allowed to expand to 80 cubic centimeters. Again, I have an initial state, I have a final state. I'm going to write down what I know, I'm going to write the ratio of the ideal gas law, and then I'm going to put in the numbers. So there are the numbers I know. Now I'm going to feed them into the ideal gas law. Now the right-hand side of this equation basically goes away because N and R and T1, which is equal to T2, are going to cancel each other out. And I'm basically back to Boyle's law again. You don't have to know that Boyle's law is P1V1 equals P2V2. Basically just work with the ideal gas law. Solve that equation for P2. And now put in the numbers and figure out what the new pressure is. I find that the final pressure was half of the initial pressure, 2 times 10 to the 4 Pascal. Last example. Example 33.4. The volume of a fixed quantity of an ideal gas is doubled, and the absolute temperature is reduced to 80% of the original temperature. What is the new pressure in terms of the original pressure? This looks kind of intimidating because I don't have specific numbers, but I can still solve the problem. Here we go. Again, let's write the ideal gas law, basically dividing the second conditions into the first conditions. The N's and the R's cancel each other out, and I can write the second pressure in terms of everything else. And now let me substitute the expression for the new conditions in for the subscript 2 things. I find when I make those substitutions and things begin to cancel out that the new pressure is 4/10 of the old pressure. So these ideal gas law problems are fairly straightforward once you catch on what to do. And we will have some more things that we'll deal with in coming lessons. For right now, that's it.